So after learning the complexation of actinides with the inorganic as well as organic ligands, we see their separation chemistry, and this has application in the nuclear fuel cycle. Now the separation of actinides in the nuclear industry mostly they're based on precipitation, solvent extraction and ion exchange, and this precipitation was used in the Manhattan project, where the plutonium separation was done by the bismuth phosphate process. And there is a schematic of this bismuth phosphate precipitation process is shown on the right side. You see that mixture of plutonium 4 plus, UO2 2 plus, and the trivalent actinides, trivalent lanthanides, and the neptunyl plus 5, and this fission products, their mixture, to which this bismuth nitrate is added along with H3PO4. You get the precipitation of bismuth phosphate. The solution goes, and all other ions actually they are coming in a solution, while this plutonium 4 plus is precipitated. This precipitate can be filtered and then redissolved to get a clear solution of plutonium 6, and then this can be again reprecipitated. That is how this bismuth phosphate precipitate of plutonium 4 is done, and plutonium 6 goes into the solution. Subsequently, the solvent extraction processes have become more popular in the nuclear industry for both the front as well as the back end of the nuclear fuel cycle. And in this case, what one needs is a extractant which is responsible for forming a complex with the actinide ion, and then which is subsequently partitioned into a diluent. So now this is the organic phase which contains the diluent, the extractant, and the metal extractant complex, whereas the aqueous phase which contains the metal ions and other impurity metal ions. Now in case of solvent extraction, I have shown a schematic where actually the mixture of two ions marked with the orange and the red color, they are initially in the aqueous phase, and you mix the two phases and then you allow to settle. You find that the red species they go to the organic phase, while the orange species they remain in the aqueous phases. So that is how this separation is done in case of the solvent extraction. So they follow the Nernst distribution law, where we have this distribution ratio, which is defined as the concentration of the metal ion in the organic phase and the concentration of the metal ion in the aqueous phase. The metal ion in the aqueous phase remains in a variety of species, including the free metal ion and the complex metal ions with the medium of the aqueous phase. That is, in case of the nitric acid medium, you have the nitrate complexes of the metal ion. On the other hand, the organic phase contains the extractable complex species, the single species, or some cases if you have a mixture of extracted species, then you have a mixed species. The extraction of the metal ions depends on the ligand concentration, metal ion concentration, aqueous phase acidity, and other conditions like the diluent composition also. Now for the metal ion extraction, the requirement is that we need to neutralize the metal ion charge, because the charged metal species is not partitioned into the organic phase, and it is mostly present in the aqueous phase because of the hydration sphere of these metal ions, particularly for the actinide ions, the very strong hydration spheres. So they can never go into the organic phase as such. It is a non-polar organic medium. And therefore, the extractant is required to form a complex, and also you need a complexing anion also. So like if you have a neutral extractant, then you need a complexing anion like nitrate ion, which makes the extracted species charge neutralized. And because of the extractant, the species become hydrophobic and it gets partitioned into the organic phase. So there are different types of extraction mechanism, that is the solvation, the ion pair, the ion exchange, and finally the chelation. The extractants can also be classified as neutral, acidic, as well as basic extractant. The basic extractants are the amines like trioctylamine or trilorylamine I have mentioned here for the ion pair extraction. The neutral extractants can be TBP, diethyl ether, or trioctyl phosphinoxide. So in those cases, you need necessarily a counter anion, that is the nitrate ion, which can form charge neutralized complex along with these neutral donor ligands. And that is how the extraction is done. In case of ether, you need to do this extraction into the organic phase by something called salting out. You have to add large concentration of salts so that it partitions favorably into the organic phase. We also have these acidic extractants. Some of them are like phenyl trifluoroacetone or STTA, dibenzoyl methane or DBM. So they are actually acidic extractants and they are existing in the enol form, and that is how they give away one proton and then form charge neutralized complex with actinide. Similar also is the case for this di2-ethyl-hexyl phosphoric acid or DEPA. This also can form charge neutralized complex with the actinide ion. It does not need a counter anion with a DEPA. In most of the cases, there are of course cases where you need counter anions with DEPA as well. Now this aliquot 336, this is actually a liquid anion exchanger. In this case, the extraction is taking place by ion exchange. That is, the chloride part of this extractant is exchanged with the anionic complex. Now coming to this extractant properties, most of these extractants should be insoluble in water and freely soluble in the organic solvent. This is the prime requirement. Otherwise, the complex will be present in the aqueous medium and not partition into the organic. There are of course some extractants which have reasonably good solubility in the aqueous medium as well, like the crown ether or acetyl acetone, which have good aqueous solubility, and in those cases the partition is there to the aqueous phase also to some extent, but major amount of the complex is partitioned into the organic phase. That is how the extraction is achieved. And this extractant should form a reversible complex with the metal ion so that you can strip it out at a later stage, so that you first have the extraction of the metal ion and then you can strip it into the aqueous phase in a subsequent step so that the overall process is complete. Then this kinetics of this extraction should be faster. If it is slow complexation kinetics, this extractant, then it will take an unusually large time for this extraction to be complete. It is not practically viable to use such extractants for application purpose. Some of these extractants should have good stability. Now, when I talk about the stability, generally it should have the hydrolytic stability. That is, should be in the acid medium. The acid hydrolysis of this extractant should not be taking place. And in case of actinides, because most of the actinides are radioactive, so the extractant should also have radiation stability. And finally, the extractant properties should be low cost and easy availability. That is how the process cost can be reduced. Now, along with the extractant, as I mentioned, we also need a diluent. So diluent should have these following properties, like it should be non-polar, it should have low aqueous solubility, it should be having easy phase separation ability, and the diluent also should have low viscosity. There are some of the diluents, they are highly viscous, like the room temperature ionic liquids. That is why it is not proposed for the separation in a large scale, because in that case the time required for separation will be much larger. Some of the extractants like aliquot 336, this is very viscous, so it needs to be diluted properly with a suitable diluent so that the extraction can be done in a favorable kinetics, so that separation can be done in an acceptable time limit. I give some example here. Actinide extraction by solvation. Now the solvation mostly is by TBP. There are also other examples of this uranium extraction by diethyl ether, methyl isobutyl ketone or hexone, and butex. So these are some of the extractants which has been used in the middle of this last century, where these uranium extraction studies were carried out in different laboratories. And this is the extraction equilibrium. What I have shown here is for the TBP, where uranyl ion, that is UO2 2 plus, is present in the aqueous phase. It can form a complex with two nitrates to neutralize its charge, that is UO2 plus 2 nitrate becomes UO2 nitrate twice. But as such, this species cannot get partitioned into the organic phase. That is why you need 2 TBP also in the organic phase, which is coming to the aqueous phase. So in such case, what happens? The TBP is partitioned into the aqueous phase, forms a complex with the UO2 2 plus 2 nitrate, this species, and finally you get this complex species, which is UO2 NO3 twice 2 TBP, which is stable in the organic phase. The schematic has been shown here. In the aqueous phase medium, we have this hydrated uranyl ion, which is forming a complex with a nitrate ion to give this type of species at 3 to 4 molar nitric acid. And the TBP, which is there in the organic phase, it can get partitioned slightly to the aqueous phase. And incidentally, TBP has a reasonably good aqueous solubility. And then this TBP present in the aqueous phase can form a complex with the uranyl nitrate, 2H2O species. This 2H2O is replaced by the TBP, and then you have this species which is present in the organic phase. Now, this is example of this phosphate complexation I was talking. This TBP is a organic phosphate. Now there are other phosphates also, like other phosphates means which are having phosphoryl groups, like in case of phosphate, phosphonate, phosphonate, as well as phosphinoxide. And these are shown in this figure, where we are comparing the extraction of uranyl ion from different aqueous conditions. Now you see here that the phosphate, that is the TBP, is giving the lowest distribution ratio values. That is, in all cases you find that the extraction of TBP is lower than the other extractants, but nevertheless, depending on the concentration, the TBP extraction can be made high. But all these cases, the concentrations are much lower. The anionic complexing ion here, in this case, it is either sulfate or chloride or nitrate. Sulfate data is not given in the figure for simplicity. But we are also studying these extraction studies at a much lower concentration of nitrate, that is 0.1 molar nitrate. That is why this extraction of uranium is very low with nitrate and TBP. But if you have a phosphonate, that is this ligand DHHP or dihexyl phosphonate, in this case you have this extraction of uranium significantly higher than that of TBP, and you get the condition where you have the TBP extraction of uranium at around 0.01, it has increased to little less than that of 1. Now same also you get for the phosphonates. So these phosphonates, they also form stronger complexes. So this BDHP, in this case, the extraction of uranium becomes significantly larger than that of the phosphonate DHHP, and you get more than 10 as the distribution ratio of uranium under the condition where the extraction of uranium was around 0.01 with TBP. So for Phosphonate, you have higher extraction, and if you go to phosphine oxide, that is trioctyl phosphine oxide, then you get the distribution ratio of uranium around 1000 or maybe little more than that of 1000. So this suggests that it depends on the basicity of these extractants, and trioctyl phosphine oxide is a strong base and it forms a stronger complex. That is how the uranium extraction is much higher with TOPO. Also, I have shown here a comparison of actinide extraction by TBP. So this trivalent actinides extraction I have shown in the right side for plutonium-3 from HCl medium, and that of americium-3 from the nitric acid medium in the left side figure. And you can see that in the hydrochloric acid medium, the extraction of trivalent actinide is significantly larger compared to that with the nitric acid medium. Now, I have discussed earlier also in one of the previous lectures, that is americium-3 extraction with TBP from nitric acid medium is very, very insignificant. And if it is possible, it is only possible by salting it out in the absence of nitric acid. So that is by taking large concentration of sodium nitrate, we can carry out the extraction of americium-3 using TBP. Now, europium also is extracted poorly, but higher than that of americium-3. So you get slightly higher extraction of europium compared to americium, maybe around 1 order of magnitude higher. But then at higher concentration of nitric acid, maybe around 5 to 6 molar, you can have a good separation of americium from europium. Thorium extraction, because it's a tetravalent ion, extraction with nitric acid is very good. And plutonium extraction, plutonium-4 plus, is even more than that of thorium because of the ionic potential. Uranium-6 extraction is much larger than that of plutonium-4 in view of the fact that plutonium-4 can form stronger complex, but uranium extraction is much higher than that of plutonium. Most part of this figure I have shown, that is because uranium-6 has 2 nitrates and plutonium-4 has 4 nitrates, and that is how under TBP present in these two species, that is uranium-6 extraction species and plutonium-4 extraction species, are 2 TBP in each case. So the hydrophobic part is same, but the hydrophilic part is much higher for plutonium-4, that is the nitrate ions. That is how the extraction of plutonium is lower than that of uranium-6. Plutonium-4 extraction is lower than that of plutonium-6. And same also for neptunium-6, that it is more than that of plutonium-4, up to maybe around 2 to 3 molar nitric acid. However, beyond that, neptunium-6 extraction is lower than that of plutonium-4, but neptunium-6 extraction is lower than that of uranium-6. That is because of the less strong complex formation of neptunium-6 as compared to uranium-6. Now, in case of the chloride medium, as you see in the right side of the figure, plutonium-4 extraction is lower, plutonium-6 extraction is higher, similar to what we have seen in case of the nitrate medium for uranium-6 and plutonium-4. But the distribution ratio values indicate that this plutonium extraction is relatively larger than that of what we see in the nitric acid medium. Now coming to the ion pair extraction, I give some example where this alamine 336, the commercial extractant, it is tricapryl amine. It extracts the uranium, which has application in the front end of the nuclear fuel cycle. And as I have mentioned, in the sulfate complexation, the anionic sulfate complexes are formed and which is extracted by the sulfate form of this amine, which is protonated. So you have R3NH plus twice and SO4 2 minus. So this type of species is there. And this here uranyl sulfate also forms an ion pair, and the sulfate from the amine part which is going to the aqueous phase, and this is soluble in the organic phase. Now increasing the alamine 336 concentration increases the uranium extraction, increasing the sulfuric acid concentration decreases the uranium extraction as shown in this figure. The solvent used is 5% alamine in 2% isodecanol, 93% paraffin. And the sulfate concentration increase suggests lower extraction, that is because of competition between sulfate as well as the anionic uranyl sulfate species indicated here. In this extraction method, isodecanol is used as a phase modifier, that is, it is used to prevent the third phase formation. We also have this ion pair extraction of actinides. I have made a comparison of this extraction of uranium-6, neptunium-6 and plutonium-6 from nitric acid medium using 10% trioctylamine in xylene. Trioctylamine again is a tertiary amine, and this data is presented in the right side figure. You can see here that this neptunium extraction is highest at a lower acid concentration, that is less than 6 molar nitric acid concentration. This neptunium-6 is extracted to a larger extent compared to that of plutonium extraction. The plutonium extraction is larger compared to that of the uranium extraction. And you get this type of curves are formed here. That means at higher concentration of nitric acid, there is a competition between the nitrate ion and that of the anionic complexes formed. So that is how this ion pair extraction of the actinides are taking place from the nitric acid medium with xylene. For neptunium and plutonium, the hexavalent state, they are forming anionic complexes to a significantly higher extent as compared to that of uranium, and that is the reason of this extraction trend. Now, another application of this ion pair extraction of actinides is the separation of trivalent actinides and lanthanides, as shown in the left side figure, where 0.6 molar alamine 336, which is a tricapryl amine, that is a tertiary amine. Alamine 336 is used in xylene, and you see the aqueous medium is 11 molar lithium chloride containing 0.2 molar HCl. HCl is added to prevent the hydrolysis of the metal ions, and the extraction of actinides is significantly larger compared to that of the lanthanides, and that is how these trivalent actinides can be separated from the trivalent lanthanides, which have relatively lower distribution ratio values. And this is used initially for the separation of trivalent actinides and lanthanides. Now, metal ion extraction by ion exchange. Here, I've given an example of extraction of uranyl ion by aliquot 336 from hydrochloric acid medium, 7 to 8 molar. Uranyl ion forms species like this, UO2Cl4 2-, and this anionic species gets exchanged with aliquot 336 chloride ion. That is what is shown here. This aliquot 336 is a tricapryl methyl chloride, and this actually, for simplicity purpose, we have shown here only 3 octyl groups here, but it can be anywhere between hexyl to octyl, the commercially available reagent. Now, the chloride of the aliquot 336 is exchanged with the UO2Cl4 2- species present in the aqueous phase, and that is how uranium is extracted using aliquot 336. Another class of this extractant is this beta diketones, which are again acidic extractant, and they form actually chelate complexes where this beta diketones like phenyl trifluoroacetam or HTTA, simply TTA, which is written here, and they form generally present in the keto form, and they are in equilibrium with the enol form, and at a given condition, the aqueous phase containing the metal ion, for example, let us take the plutonium ions, then this enol form of TTA forms a complex with the plutonium ions, and that is how the plutonium ions can be extracted into the TTA medium. So, by adjusting the conditions of the aqueous phase, this plutonium extraction can be achieved. If you are having plutonium in the +4 oxidation state and your aqueous phase is 1 molar nitric acid, then only plutonium-4 will be extracted. So that is how the plutonium-6 and plutonium-3 species can be left behind in the aqueous phase. Now, subsequently, if you want to extract the plutonium-6 from the aqueous phase, leaving behind the plutonium-3, then you adjust the pH of the aqueous phase to 2. That is how, by TTA extraction, plutonium-6 can be separated from the aqueous phase, and finally whatever you are having in the aqueous phase is the plutonium 3, or you can simply extract the plutonium 3 into the TTA phase by pH value around 4 to 5. So if you go to beyond pH 6.2, then it will have hydrolysis of TTA as well, and that will create problem for the metal ion extraction. Now finally we come to the reprocessing of the spent fuel, which is the application of the TBP extraction, and I have discussed for uranium and also for plutonium. So this process is called the Purex process, or plutonium uranium redox extraction process. Now where actually this TBP, the structure which is given here, it forms a complex with plutonium 4 and also uranium 6, that is the uranyl ion, and both these metal ions are extracted into the TBP phase, which is taken in end-O-decane. And the major advantage of this Purex process is that the organic solvent containing the TBP, it extracts only uranium 6 ion as well as plutonium 4 plus ion, and then these are extracted, leaving behind the fission products like cesium plus, strontium 2 plus, and also the trans-plutonium elements like americium 3 plus, curium 3 plus, etc. And fission products, they contain most of the rare earth elements also. That is how these trivalent actinides and lanthanides are directed to the radioactive waste stream. And the separation scheme is actually the co-extraction of plutonium 4 and uranium 6 by the TBP. And in a subsequent step, this plutonium and uranium partitioning is done by reducing plutonium to the plutonium 3 oxidation state. So now the steps we'll be discussing in the next slide. But here one thing I would like to mention, that only 30% TBP is used, because if you use higher concentration of TBP, then there are problems like there will be viscosity of this medium increased, and also the metal ion loading can be significantly higher, and that will create problem in the operations in the plants. So the major problem in case of this, that TBP undergoes radiolytic as well as hydrolytic degradation on continuous use in the plant, and the degradation products of TBP are the monobutyl phosphoric acid or the dibutyl phosphoric acid. They form strong complexes with plutonium, and that is how it is not possible to recover plutonium from the extracted phase. So because of that, this degradation products, that is the MBP and DBP, they can be separated from the TBP phase by giving a alkali was, the sodium carbonate was. That is how this is removed, and this TBP can be recycled. And subsequently, after a long time after it is used, this TBP, which is a spent solvent we can call, this is again given for the cementation in the waste management. So that is how this TBP is finally separated from this plant. And also this kinetics of this extraction of uranium and plutonium is relatively fast. TBP is non-toxic and it has a very low cost. In view of this several good physical properties, this TBP is used in the reprocessing plant worldwide last several decades. And also one of the major advantages of the TBP is that this decontamination factors for fission products are very, very high. Now the schematic of the Purex process is given here, that you have the spent fuel and which is dissolved, and the fluid adjustment is done to 3 molar nitric acid. And finally the plutonium valency adjustment is a must. So plutonium, as you know, it exists in different oxidation states like +3, +4, +5 and +6. But +5 stability is much less because of the disproportionation. That is how this plutonium 3 and plutonium 6, they are actually adjusted to plutonium 4 plus oxidation state by the nitrite ion, as shown here. You get this nitrite ion by dissolving this NO2 as shown here in the first equilibrium, and in the second one the plutonium 3 plus is converted to plutonium 4 plus, and the third equilibrium shown here with plutonyl ion, that is PuO2 2 plus, is converted to Pu4 plus as well. So nitrite ion is actually doing the dual role That is, it's oxidizing plutonium 3 plus and also reducing plutonium in the plus. Using 30% TBP, the organic phase is having both uranium and plutonium as the expected species that I have already discussed before. Now, subsequently, the aqueous phase, which is coming out of this extraction cycle, this will have all the fission products and also the trans plutonium elements like americium, curium, etc. Then this organic phase containing the uranium and plutonium extract in TBP. This is actually given a partitioning state where uranium 4 plus is passed and then plutonium 4 plus is reduced to plutonium 3 plus. So it goes to the aqueous phase, and then uranium which is there in the organic phase is subsequently recovered and then used for the subsequently.